Good morning, everybody. Thanks for sharing this webinar. We are waiting for all the attendees to join us. I'm Serena from ACR Plus. With me, there's my colleague Paolo.
Good morning, everyone.
And we will just introduce some technical information about the platform, GoToWebinar. And then we will give the floor to Susanna from Phoenix to talk about the webinar, introduce you the topics of the webinar. Okay. Good morning, everybody. So we start the webinar of the first webinar of RE4 Project. And I see that some attendees are joining the webinar, so good. Thanks for joining us. And I'm Serena from ACR Plus, with me Paolo, my colleague.
Good morning, everyone.
And we will open the webinar just explain you some technical information about the platform. And then we will give the floor to Susanna from Phoenix to explain you something about the webinar of the project and introduce you the panelists. So about the platform, please, you can notice on the panel that you can ask some questions. Just go into question and write your question there. So we will receive it and we will have time to answer to your question at the end of the webinar. Please just write when you write your question, just define to who you want to do your question. So if you are interested to talk with Alessandro, just write that that your question is to him. So we will just forward the question to him. And then if you are having some technical problem, like you cannot hear properly, just write it down on the chat, and we will try to help you. So thank you for joining us. We can start our webinar. So I give the floor to Susanna. Thank you.
Good morning, ladies and gentlemen. I'm very glad to welcome you to the first webinar of the European research project RE4. In the following 3 months, you will be able to join us for a set of 4 webinars. The next one will be on the 18th of December, then one in January, and the last one in February. My name is Zuzana Taťáková, and I'm representing Phoenix TNT, Dissemination and Exploitation Leader in the RE4 project. Today we have 3 presentations on the topic of solutions for high-quality recycling of construction and demolition waste. You can see the agenda of today's webinar on your screen. And now I would like to welcome our first speaker, Mr. Alessandro Largo. He is the project coordinator of the RE4 project and the head of the Resilient and Sustainable Civil Engineering unit in SETMA. And Alessandro will present the RE4 project to you. Please join me in welcoming Alessandro.
Well, good morning, ladies and gentlemen, and thank you very much for attending this session related to solution for high-quality recycling of construction demolition waste. And also thanks a lot to Susanna for the introduction. Today, I will introduce the RE4 project, that is a European-funded project of circular economy in construction. Before I get to the heart of my presentation, I would like to briefly present CETMA, that is an Italian RTO founded in 1994 and located in Brindisi, South Italy, with skills on materials engineering, industrial design, and ICT. Our industrial priorities are materials and construction, transport, productive system, energy, and healthcare. So coming back to the RE4 project, it is a project of circular economy for the construction industry, which is according to the last available key figures from the European Construction Industry Federation. It is one of the main drivers of the European economy, accounting for more or less 90% of the European gross domestic product, with 10 billion euros of turnover and 6.5% of total employment. However, construction industry is also responsible for the main waste stream at European level, the construction demolition waste, which accounts for approximately 800 tons per year. The interesting point is that quite a lot of those construction demolition waste can be recycled in high-grade application, but they are very often confined to low-grade application or landfill. Moreover, there are other materials from construction demolition waste, I mean wood, plastics, and glass, with a very high recycled potential that is, however, unexploited. So, in this scenario, Europe has set the challenge of the development of energy-efficient building concept using new or adapted prefabricated components, allowing the reuse and the recycling of different materials and structure while reducing energy use and minimizing environmental impacts. Europe also set the targets of a minimum share of recycled materials in the final product of at least 10 to 15%. This challenge was taken up by the RE4 project, which has developed a fully prefabricated, energy-efficient, easy dismountable, and reusable building made of concrete and timber components containing up to 65% by weight of CDW derived materials and structures. And to reach this goal, we gathered a multidisciplinary consortium coordinated by CETMA and made of 13 partners from 7 different countries across Europe and 1 non-EU country, comprising 5 among university and research center, 7 industrial partners, and 1 association. The project has an overall budget of about 5 million euros. It started in September 2016 and it will end in February 2020. There are 4 main pillars supporting the project. The first 2 are technical and refer to the maximization of CDW recycling and reuse. In terms of construction demolition waste recycling, RE4 has developed advanced CDW sorting technologies to improve the overall quality of CDW derived product, as one of the main constraints for growth is the quality, not good enough when compared to virgin sand. At the same time, RE4 has also fully exploited the recycled potentials or lightweight fraction from construction demolition waste, which is currently unexploited when it comes to rigid plastics or wood and plastics. This has been supported by the compliance assessment of each sorted fraction against relevant national and European specification, with the definition of new quality classes for CDW-derived aggregates with the aim to support the development of a new standard in the field of construction demolition waste. As final, the construction demolition waste recycling potential has been verified with the development of RE4 materials and prefabricated elements incorporating high ratios of construction demolition waste derived materials. RE4 aims to improve the state-of-the-art recycling rate from 80% to 95% and to improve resource efficiency in terms of virgin material replacement of at least 65%. In terms of reuse, RE4 has developed new sustainable strategies for the disassembly and reuse of concrete and timber structure and building components that reach the end of their service life. Moreover, RE4 has developed innovative design concept for a fully prefabricated, easy dismountable RE4 building with up to 90% of reusable structure. The concepts have been designed in such a way that multiple applications for different building typology, for example, residential or commercial, will be easy to implement. The RE4 elements have been designed to be easily tailored to different climatic as well as structural requirements of different geographic zones across Europe and outside the EU. Well, these are the goals from a technical point of view. However, we know that it is not enough to push the EU to the forefront in the area of the CDW management. But also other non-technical barriers have to be tackled as well. The first one is related to the overall management of the CDW value chain. By tackling the CDW management at different level, RE4 aims at contributing to reach the target of recovery recycling CDW by 2020. This is built upon the proper stakeholder engagement since the beginning of the proposal preparation and upon the development of a BIM-compatible DSS tool to support owner and construction demolition companies by providing an estimation of the types and quantity of CDW that will be generated during construction demolition with possible utilization option and related logistic references. This new approach to the CDW management will also generate new attractive business opportunities as well as new technical skills like CDW managers. The second one is related to the end user acceptance. It is well known that people do not want to hear about materials from waste, and the RE4 proposed many technical and non-technical activities in order to increase end user acceptance in the use of secondary raw material. This is built upon LCA, LCC, and social LCA analysis, HSE analysis, performance assessment, certification, and standardization strategies. Finally, training videos will be provided for all the most relevant activities of the RE4 and will be used for student and new young technical profile like CDW managers. Now let's see a brief overview of the main results obtained so far by the RE4 project. To each result, we have devoted specific presentation both today and in the forthcoming webinar session. So it is possible to build a fully recycled house? The RE4 project answered yes. Nevertheless, it is crucial to adopt a circular approach and to address all the main steps of the construction process. That's why the RE4 project has developed a solution in terms of design for reusable buildings, the construction strategies, CDW sorting, CDW quality assessment, development of materials and prefabricated components incorporating high ratios of construction demolition waste, digital tools to support all the actors of the CDW management. All of the RE4 solutions have been then demonstrated and validated in a real environment in 4 RE4 demo buildings. Here you can see a picture of the Spanish RE4 demo building, a 2-story building made of prefabricated concrete and timber component, fully reusable and with a replacement rate of virgin materials in the range of 50 to 85%. In terms of figures, the RE4 project has developed one set of statistics, both lessons learned and recommendation in terms of CDW management, 4 new technologies in terms of deconstruction, sorting, design, and digital management, say 6 new solutions at material level in terms of new quality classes for CDW derived aggregates, and 5 new materials incorporated on average 78% of CDW, 8 new components, both structural and non-structural, incorporating on average 82% of CDW, and finally 4 demo buildings, 2 for new construction and 2 for renovation. Then we have tried and we are trying to share as much as possible these results, as we feel that the transition from a linear to a circular economy in construction has to be promoted at all the levels of the CDW management value chain. In terms of impact, the European Commission set the goal of CO2 saving by 30%, energy saving by 20%, and minimum share of recycled materials in final product of at least 10 to 15%. These are the results that we obtained with the RE4 project. So CO2 saving more than 40%, energy saving more than 45%, and replacement of virgin material with the CDW materials more than 50% on average. We've also provided an additional impact, an economic impact, because the RE4 solution resulted to be more than 50% cheaper than conventional solution. So to conclude, the RE4 project has demonstrated how CDW derived materials extraction can be effectively reintroduced in the production cycles of concrete and timber components with a replacement rate of 15 to 85%. Moreover, from a technical point of view, a fully prefabricated 100% reusable building is now a reality. The way is paved, but there is still a strong need of improved waste identification, separation, collection, source, quality assessment procedures, and mainly policy and framework conditions that can foster the transition to a circular economy in construction. Thank you very much.
Thank you, Alessandro, for your introduction to the RE4 project. Our next presentation will focus on innovative sorting system based on automated robotics, and it will be presented by Tommaso Zerbi. Tommaso is a project manager in STAM, and his main focus is on industrial process automation, material recognition, and robotic applications. Tommaso, the floor is yours.
Thank you, Susanna, and good morning to everybody. My name is Tommaso Zerbi. I am project manager in STAM, an engineering company based in Italy, and I am going to present the sorting system for CDW based on robotics technologies that we have developed in the context of RE4 Project. Basically, we started from an environmental need formalized by the European Commission, which in its waste framework directive, which required all the member states to reach by the end of next year, 2020, a target of at least 70% of recycled or reused CDW by weight, talking of course about non-hazardous materials. At the time of starting the project, the situation was a little bit different, and the average recovery rate for the member states in Europe was around 50%. And the main issue was that these materials were recovered and reused only for low-grade applications, such as load bases, for example. Then the development of this robotic sorting system defined 3 different objectives in the context and in a streamline with the objectives of the project. The first one is contributing to define, together with the other technologies developed within RE4, a complete circular management system for CDW to design a process from the demolition of buildings up to the construction and building of new ones. The second one is more focused, of course, on robotics sorting systems, is the enhancement of the technical and economical value of secondary raw material derived from CDW if compared with the state of the art of technologies. And the third one is giving to these secondary raw materials a new life designed within the project. For example, a new life talking about high-grade applications such as structural concrete or geopolymer binders and insulating prefabricated panels, according to the different classes of materials that can be sorted by the systems. STAM was allowed to accept the challenge of this research activity thanks to some background expertise. The main one is the expertise in designing and integrating complex robotics and mechatronic systems, coupled with other knowledge in software development, in particular for image acquisition, image processing, and three-dimensional image processing, and in the development of recognition and classification algorithms. These expertise were previously already applied into another sorting system for toys industry, where we went to develop a line, a robotic line, to separate different items in an automatic way according to the different shapes that were automatically detected. The first activity within this task of the project was the definition of the specification, functional specification and technical specification for the sorting system. Some of them were qualitative, such as, for example, the list of materials to be classified, which were identified as the bricks, the stones, and the mineral aggregates, the ceramics, glass, plastics, and wood, and the working mode for the system, which had to be, of course, fully automatic. And some of the specifications were quantitative, such as the peak rate aimed at reach 100 peaks per minute, the minimum payload of the mechatronic part, the maximum contamination by weight of each single class, around 5%, and a productivity of at least 100 kilograms per hour. After defining these specifications, we went to the definition of a layout for the system together with the design concept. You can see in the upper side of this slide the top view of the layout. On the right part of this top view, there is the inlet side of the material. The concept is composed by a conveyor belt on which the CDW fragments can flow and are analyzed by the first system they encounter, which is the vision system and the sensing system of the robotic cell. This sensing part is composed by an hyperspectral camera which scans line by line and pixel by pixel the belt flowing under it, and is aided by a suitable illumination unit emitting a certain power of light in the near infrared range. The sensing system gives the raw data, the raw signals to the processing unit, which is composed by an industrial PC on which the software modules are running and which has three main tasks. The first one is acquiring and processing the images and the hyperspectral images. The second one is classifying the information in real time and classifying the detected fragments upon the conveyor belt. And the third one is giving commands to the mechatronic part. This last part of the system, the mechatronic part, is composed by a 6 degrees of freedom anthropomorphic robot and an end effector based on the vacuum technology. The aim of this mechatronic part is performing pick and place operations on each single CDW fragment on the conveyor belt by picking them and putting them in different boxes according to the material class they belong to. Here we can see a scheme of the software architecture of the system. This architecture was developed in ROS, Robot Operating System Environment, and is composed by different nodes which are represented by the ellipses in the slide. The first node, according to the data flow, is the camera gate, which was developed by the camera software development kit, and which produces the raw data in the form of the data cubes. Each single data cube represents a frame of the conveyor belt, so an image, like the normal RGB images we all know, but with the difference of the number of channels. An RGB image has three channels. Our images have 252 channels or different wavelengths. These data cubes are passed to the image processor node, which cooperates together with the classifier node. The image processor detects and analyzes the geometrical information by doing a segmentation of the frame and detecting the CDW fragments within the image and calculating their center of gravity. Moreover, it communicates together with the classifier. The classifier loads the classification rules from database and extracts the most important features of the pixels which are given to it by the image processor, and does the real-time classification of the pixels. So gives to each pixel, to each single CDW fragment, a label corresponding to the material class it's supposed to belong. So the image processor, after the label assignments, publishes the geometrical targets to be given to the mechatronic parts. These information are geometrical and correspond to the points to be reached by the robot to do the pick and place operations. These information are given to the decision maker node, which evaluates the possibility of the robot to effectively reach the CDW within the working space of the robot, according to the position and to the other fragments to be reached, and to the speed of the conveyor belt. And finally, this node defines the path the robot has to follow to do the pick and place operations, and gives the target positions, the sequence of the target positions to the robot controller. We can see now in a little bit more detail the image processor node. In the upper part of this slide, we can see a grayscale image and a color image. The first things that the image processor does is selecting one layer, one channel of the data cube I was mentioning before, and uses this sort of grayscale image to do the segmentation of the frame and to detect the fragments on the conveyor belt. By doing this, after doing this, it calculates the center of gravity of each single fragment, which is represented by the colored bullets in the right part of the picture, and identifies around the pixel of the center of gravity a window of reliable pixels which are passed to the classifier. And the classifier will make these pixels, which are 10 pixels, make a votation to define which is the most voted material class to be assigned as a label to the fragment. And finally, the image processor tracks the objects into the frame according to their position and to the speed of the conveyor belt for the later pick and place operation by the mechatronic part. The other most important node of the software architecture is the classifier, which uses the raw data. In the lower left part of this slide, we can see how the raw data can be represented. For each pixel which are analyzed, we can see a line, graph, representing the wavelength signatures of the pixel. As we can see, different materials can be characterized by quite different shapes of these wavelength signatures. And the aim of the classifier is finding a formal mode, a mathematical modality to identify these shapes. The first operation that we did by developing the classification model was to reduce the dimensionality of the problem. The problem was its beginning a 252 dimensions problem, one for each wavelength represented into the data cube, the raw data, and this would be a too heavy problem from a computational point of view for the normal hardware. So we adopted a linear discriminant analysis method to find a linear combination of the features to separate and to characterize the different classes. So by this linear discriminant analysis, we were able to reduce the problem from 252 dimensions down to 15 dimensions. So by achieving a much lighter problem to be processed by our hardware. After that, we did a normalization of the samples with a combination of different algorithms, such as the Tomek-Links algorithm and the K-means, with the goal of cutting the pixels which are very different from the other pixels belonging to the same class. So in other words, to uniform the classes within the space of the problem. And finally, the real classification was done by adopting a linear kernel support vector machine, which is aimed to find a linear function within the multidimensional space of the problem, which is to separate the pixels belonging to the different classes by specific mathematical rules. After this development part, we went through quite a long test campaign, two different test campaigns actually. One is represented by the pictures you can see in the right part of the slide, were tests done at lab scale. And the other one, you can see in the left part, were done in an relevant industrial environment hosted by our partner CDE, and where the system faced with real industrial problems such as dust, the presence of dust, noise, vibrations, and humidity, and so on. And in both the test campaign, we were able to underline quite encouraging results. Basically, we at the end developed two different classifiers. The first one dealing with the heavyweight materials, the brick, stones, and mineral aggregates, ceramics, and glass. The second one working with lightweight materials such as plastics and wood. And we reached a productivity around 800 picks per hour, and with a classification error and pick and place error which are very low, around 1%. So even better than what requested by our starting specifications. Few words about the future possible developments of this system. We can, of course, still improve the proof of concept that we have developed. For example, by testing the system and by integrating into the software architecture different methods than the support vector machine. For example, the neural networks and the convolutional neural networks, which are widely used in both research and industry for image processing and object detection problems and pattern recognition problems. For, of course, with normal images, with grayscale images and RGB images, and we can, of course, test if they can well work even with hyperspectral images. The second activities that can be done deals with the industrial upscaling of the sorting system by giving it a more industrial look, by integrating more industrial element, PLC, by integrating safety measures, human-machine interface, and so on. And by increasing the performance of the system, of course, in terms of productivity, for example, by integrating multiple pick and place operations, multiple robots on the same line, and so on. And that's it from my side. Here you can find my contact if needed, and thank you. Thank you very much for your attention.
Thank you very much, Tommaso. Our final presentation will be on the topic of concrete mix design, and it will be presented by Marios Soutsos. He's a professor of structural materials at School of the Natural and Built Environment at Queen's University in Belfast. So, Marios, the floor is yours.
Thank you, Susanna. Can you hear me? Hello, can you hear me?
Yes, we can. You can start.
Okay, that's lovely. Okay, my name is Marios Sitsas. I'm a professor of structures at Queen's University Belfast, and we are one of the many partners for the RE4 project. So I'll be presenting the use of construction and demolition waste derived aggregates in concrete mixes. So when the project started, we approached our industrial partners to see what their requirements were, what concrete mixes they were using, to see how we could achieve high replacement levels of the virgin, newly quarried aggregates with construction and demolition waste derived aggregates. So the industrial partners were using different types of concrete mixes and different materials. So the presentation is structured around these different types of concretes, listed here as one being self-compacting C40-50 concrete, vibrated C25-30 concrete, lightweight concrete, which we try to achieve using recycled plastics, and wooden plastic mixtures. We also did cementless concrete, which is alkali activated binder concrete, which is a C25-30. And finally, we looked into concrete building blocks that require a dry mix of concrete. So I'll be going through each one of these in my presentation. So in terms of the concrete mixers from the industrial partners, you can see that there is the self-compacting concrete with 28 days strength complying with the C40-50. You've also got the cement type that is being used. So some like the SCC and some others were using rapid hardening, while others were using normal hardening cement. We've got a vibrated concrete, two strength grades, C25-30 and the C32-40. So where these mixes, original mixes came from, are listed on the right-hand column of the table. So some of the mixes came from CREA in Northern Ireland, and some came from Acciona in Spain. We also produced lightweight concrete, as I said, with plastics or a mixture of wood and plastic, and that was aiming to have a low density and a good thermal conductivity. The strength requirements for these lightweight concretes were low. So construction and demolition waste is an inert fraction, and it has to be processed before it can be used as aggregate. So the mineral fraction was sorted into fine aggregate, 0 to 2 millimeter, and then two sizes of coarse aggregate, 2 to 8 millimeters and 8 to 16 millimeters. They were used for self-compacting concretes and vibrated concretes. The lightweight fraction was the rigid plastic that required sieving because of the large particles, and we also used mixed wood and plastic as fine fraction. So a few pictures showing the aggregates, the fine aggregates, 0 to 2 millimeter, the 2 to 8 millimeter, and the 8 to 16 millimeter. What one can see from these pictures is that the aggregate we have is a mixture of masonry, the red particles, and then we've got the aggregates as well as aggregates covered with cement paste. But because of the separation plants that are being used, developed by CDE Global, the aggregate is relatively clean. In terms of wood and plastic, you can see that in the top picture. In the rigid plastic, you can see large particles. And as I said, these had to be sieved in order to get the size of aggregate that we required for the lightweight aggregate concrete. So the first type of concrete we looked into is the self-compacting concrete. So initial tests, screening tests, indicated that if we used both coarse aggregate and fine aggregate, then the strength of the concrete gets reduced. So the right-hand side column, the C6, you can see that the strength, the 7-day strength was about 38, while with only using coarse aggregate, the C2H mix, the 7-day strength was 48. So there is a reduction from using recycled aggregates. If you use both coarse and fine, the reduction is bigger than if you use only coarse aggregate. But all of these initial tests were labor intensive, and there were about 22 different mixes that were trialed. So a graph showing the compressive strength versus the age. They were tested up till 7 days, just as I said, to see the effect that the recycled demolition aggregate was going to have on the compressive strength. So the ones showing 28-day strength as they are the ones with the newly quarried aggregates, and you can see that strengths above 60 megapascal were being obtained. But once we started replacing 100% of the newly quarried aggregate with recycled aggregate, then the strength dropped to slightly below 50 megapascal at 7 days and dropped to below 40 megapascal when both fine and coarse aggregate were used. Compressive strengths we obtained, as I said, there was an early age requirement at 16 hours because Crea Concrete is using it for precast work, and 16 hours is when the structural elements are lifted off the heated bed. So there was a requirement of 15 megapascal at 16 hours, and this was achieved easily. 28 days of 48 megapascal were being achieved. So some slight modification was needed to this mix to increase the cement content, increase the SP, to increase the strength further. Mechanical and durability properties of all the concretes developed have been determined to ensure that they are compliant with all the relevant standards. So the table shows the drying shrinkage of the concretes, the flexural strength, the modulus of elasticity. Chloride migration tests were carried out, as well as freeze-thaw resistance in presence of de-icing salts. So the full range of certification tests were done. So moving on to the second type of concrete, which is the vibrated concrete. Again, some initial screening tests were done with 100% replacement with recycled demolition aggregates. So compressive strengths that were achieved varied from very low 20 to over 44 megapascal. Hardened densities are affected if you have masonry particles in the recycled aggregates, so strengths and densities are related. So from those screening tests, selected mixes were done in large batches. So we've got the consistency classes S3, S2, and the mix 10 as S2, S2 class. Strengths are 3 days, over 28, and strengths at 28 days, especially with the second trial, we have achieved 50 megapascal concrete, which was suitable for the C2530 class concrete we are aiming for, but also for higher strength classes C3240 and C4050. So moving on to the lightweight concretes, again, initial tests with rigid plastic. We have the aggregate, the cement, the water, the additive superplasticizer was used. And as you can see, there is a high percentage of air voids in them. They all had to be flowing concretes. Again, the same thing, initial tests with a mixture of wood and plastic. And you can see the wood and plastic in the cut section. In terms of compressive strengths obtained, the compressive strengths with the rigid plastic was 7.7 megapascal at 28 days. There is a column saying the target application, its panel layers, and the compressive strength at 28 days can be anything between 4.5 and 24. So with the mix 11, the wood and plastics, the compressive strength is near the lower part of the range, achieving only 4.7. However, these are for thermally insulating concretes, and therefore what is important is the thermal conductivity of these concretes, which was measured and was found to be below 0.31 and 0.29, which are towards the lower range, part of the range that is normally required, which is 0.16 to 1.0. The alkali activated binders, we've got the full-scale mix and tests. This is without using cement, so instead fly ash and a GGPS was used. So total binder content was 440. Again, I repeat, there was no cement, it was just fly ash and gram granulated blast furnace slag. We used 50% newly quarried sand and 50% recycled sand. The coarse aggregate was all recycled aggregate. Activator was sodium silicate, and the strengths obtained were from 20 to 33 megapascals. Again, with the alkali activated binder concretes, all the necessary durability tests were performed. This one is showing the freeze-thaw cycling, and it shows the specimens that are degrading after the freeze-thaw cycles. So freeze-thaw, The other one was carbonation depths. So we've got at the top, we've got the recycled aggregate concrete, and at the bottom, this was compared with the control mix, which was with the newly quarried aggregates shown at the bottom. As well as carbonation, we've done chloride penetration, and as you can see, the virgin aggregate had slightly lower chloride contents by mass of concrete than the recycled aggregate alkali activated binder concrete. The final mix developed is the dry mix for concrete building blocks. The aims was to assess the impact of construction and demolition waste derived aggregates on the semi-dry mix used in the production of these building blocks. So we have used the lab scale vibro compaction technique to replicate the manufacturing process, and you can see the rig in the first photograph on the slide, whilst you can see the building blocks produced in the laboratory on the top right-hand photo. The requirements for these blocks was a compressive strength greater than 7.3 megapascal at 28 days. This is what's required by the Concrete Block Association in the UK. Our target was a construction and demolition waste derived aggregate content of 100%. The bottom picture on the right shows the equipment, machines used in Northern Ireland. They are what we call egg layers. They are not static machines, they are moving machines. So upscale factory trials were performed. So from the experiments done, initial tests with 50% level of replacement of newly quarried aggregates with recycled aggregates. The 7.3 megapascal compressive strength was achieved easily, but when we went to 100% replacement, the strength dropped to below 7.3 megapascal. So to achieve higher strength, we experimented with increasing the cement content from 119 kilograms per cubic meter to 153 kilograms per cubic meter. We looked at the void content. Building blocks are not fully compacted. 19% is air. So we tried to reduce the void content from 19% to 15% and 11%. And by reducing the void content, the air, and increasing the density, the strength increased. We do understand that this is not the favored option for the building block producers. They do not want the density or the void content of their building blocks increased. So these are the different types of concretes that we've investigated, and as part of the project, it has been demonstrated that construction and demolition waste derived aggregates can successfully be used in lots of different types of concretes, which are listed in the slide: self-compacting, vibrated, lightweight concrete using plastics and wooden plastic mixtures. They can be used in alkali activated binder concretes, and they can be used in dry mix concretes used for building blocks. I would like to thank you for your attention, and I'll be happy to answer any questions that you may have during the question time. Thank you.
Thank you very much, Marios, for your presentation. As we have finished with all the presentations today, I would like to thank the presenters. And it is now time for questions. we have received some questions, and I will now ask them to the presenters. First question is for Marius, and the question is, what was the biggest challenge in your investigations of concrete within the RE4 project?
I think the challenge was to get 100% replacement by newly recycled aggregate. Recycled aggregate, as I said, tend to have it to be a mixture of aggregate, old concrete, and masonry, red brick basically. The density of these aggregates is lower than newly quarried aggregates, and by using them there is a detrimental effect on the strength, and therefore, as I included in the presentation, there were different approaches to achieving the strength or maintaining the strength required by the factories, by either increasing the cement content and reducing the water-cement ratio, or in the case of the building blocks, was by increasing the density of the building blocks and reducing the air in the building blocks. I hope that has answered the question.
Yes, thank you very much. We have another question. This one is for Tommaso. What are the important factors for waste management on site in order to diminish waste and increase recycling and reuse? So the most important factors.
Yes, talking about our sorting system and how we designed and how we realized it, I think that the most important thing is specifying really precise input material requirements to make the system, the robotic system, working properly. So I didn't mention in the very summary, summarizing presentation, but we have defined a set of specifications for inlet materials according, for example, to the minimum and maximum size of the fragments. So and to the level of cleanliness and dryness of the CDW. So basically, I think that on site, in order to make such a technology working properly, the CDW should have been previously treated in order to have a low level of dirtiness on the materials and to have some dimensions which are suitable to be processed by the robot. Otherwise, we have to redesign the system by taking the same concept, the same technologies, but with different elements. For example, a different conveyor belt, a different robot with different payloads, and so on.
Thank you very much for your answer. And we have one final question for Alessandro. What do you consider the biggest achievement within the RE4 project so far?
Well, this is a good question. There are several achievements in the project so far, but I think that it was a continuous process that started from the lab and passed through the industrial upscale, industrial production, and all the RE4 results in terms of sorting, in terms of digital management, in terms of industrial production of prefabricated components in terms of design has been integrated and showcased in real size buildings. So I think that our demo buildings, our pilot buildings are the main results, because it takes into account all the results that we have developed during the project. They are very close to the reality. One of them, the one located in UK, will be used effectively by our partner CREA, because they will use the RE4 building for their new laboratories, and this is for sure a big result, I feel.
Thank you very much. Thanks to all the presenters, and thank you to the audience for the question. It was a great opportunity to hear from the partners of the project. I would like to invite you to the next webinar, which will be on the topic of prefabricated building elements incorporating up to 100% of CDW. You will hear about the different elements which are produced within the RE4 project. Also, we would like to invite you to a workshop which will be held in January in Madrid. It will be the final workshop of the project, and you will be able to join us on the demo site and visit the demo site in Spain. So thank you very much, and don't forget to register on the website for the next webinars. Thank you and goodbye.
Thank you for everybody. The webinar is finished. Just one last reminder that this webinar session has been recorded, so we will publish the link for the audio and to download all the presentation on the website. So follow the project and see you to the next webinar. Thank you for everybody.